Okay, folks, so we've talked about vector spaces a couple of times already. It's time to actually introduce them formally with a definition. We're not going to do too much more than give the definition and look at a couple of examples and discuss the properties. In some later exercises, we'll actually look at proving a certain collection of objects forms a vector space. We'll look at how we determine subspaces, etc. But for right now, I just want to get some of the terminology out of the way and give you a chance to digest it. Also, we'll be using this terminology when we start talking about linear transformations. So let's go ahead and get started. So what is a vector space? Well, a vector space is a collection of ordered quadruple where we've got four different components: a set V, a set F, something that we mean by addition, and something that we mean by scalar multiplication. Okay. So this set V is a set of objects. This is a very abstract definition. It's a set of objects called vectors. Okay. And you could think of these as matrices, you could think of these as numbers, you could think of these as functions. Okay. This is a very general definition. Okay. And then F is another set, is a field. Okay. We're not going to worry about defining a field in here, but you should know that it's a collection of objects that behave very nicely, in that you've got something akin to multiplication, and you've got inverses to that multiplication for everything but the zero element, and you've got something akin to addition that works very, very nicely. So anyway, don't worry about that too much, other than to say that the fields that we will usually use are R or C in this class. Okay. Then addition and this scalar multiplication are binary operations. That word binary operation sounds a little intimidating. It just means that you take two objects and do this to them and return a new object. Okay. So let's go ahead and look at those two operations a little bit more. So let's say we've got three objects sitting in the space that we want to call a vector space. So we've got three vectors, u, v, and w. Okay. Then what happens with this operation of addition? Well, suppose I give you u, vector u plus vector v. What we need to ensure is that when I add these two things that I'm calling vectors together, I get something that's again in the set. So we've got to get an object that's back in our set. So this is called the closure property of vector addition. Okay. That word closure is a little bit confusing. Let's look at an example that might clarify. Let's suppose we have the set O is the set of odd numbers. Well, I might be trying to form a vector space out of the set O, but if I use what I traditionally think of as addition, so for example, if I take the number 3 and add it to the number 5, that's an odd number, that's an odd number. So notice both 3 and 5 belong to our set O, but the result when we do that addition is the number 8, which was not an element of our set O. So the odd numbers don't form a vector space using this addition as we would normally think of it. So we would say that O is not a vector space because it's not closed under vector addition. When I added two vectors, I didn't get something that was also in that set. Okay. The other closure property that we have says if I take a scalar from my field and multiply it to the vector through what I mean by scalar multiplication, I need to get a result that is also in the vector space. From here on out, I won't ever write that dot. I'll just butt it up against the u. But I'm working with that operation dot, that scalar multiplication. So this property is called the closure property. The closure property of scalar multiplication. So again, let's look at an example of something that's not closed. If I looked at the set of E, which is my even numbers, okay, and so what's an example of an object that's in my even numbers? Well, that maybe is a number, notice that, say, 6 is in E. If I take any old scalar from the real numbers such as, I don't know, such as 1/2, and I multiply that scalar 1/2 to 6, notice I get that 3, and 3 is not an even number. So the scalar 1/2, when I multiplied it to 6, under what I normally think of as multiplication, did not give me something that was in the original space. So the even numbers are not closed under scalar multiplication. Okay?